So now that I've shown you one use of integration and integrals in literally reversing differentiation, there is one more rather fundamental use of integration. It's probably the most famous use of integration, and that is in finding the area enclosed by a function and the x-axis between 2 points. So say I've got an arbitrary function here, y equals f of x, independent to all of this. So for any graph y equals f of x, I'm going to denote a new function, a of x, or capital A of x. And that is going to give me the signed area enclosed by y equals f of x and the x-axis from 0 to x on the x-axis. And what I mean by that is, say I've got a point here, that means this whole area is a of x from 0 to x. As I've now defined a of x to be the signed area, I first must discuss what a signed area is. And what a signed area is going to be, rather than this area being positive, this area is going to be counted as a negative area. So if I wanted the area from this point to 0, it would be the sum of these two areas minus this area here. It's a negative area. Or we're adding all three areas, but this area has a negative value. Well, first and foremost, I know for a fact that a of 0, according to this, is equal to 0, because we're looking at the area, doesn't matter if it's signed or not, it's enclosed by the graph and x-axis from 0 to 0. If anything, it's just a one-dimensional line. We're lucky here that it literally is at point 0, but say I wanted the area from x to x. A one-dimensional line has no area. Its width is 0. So I know that a of 0, according to this definition, is going to be 0. And in truth, I could define this lower bound of 0 to be at any odd point, but 0 just seems to be the most natural one. So what can I do from here? Well, let me draw another perpendicular line to the x-axis at a point, an arbitrary point x plus h. That means this whole area now is equal to a of x plus h. So this mini area here between these two dashed perpendicular lines to the x-axis is the area of a of x plus h minus a of x. And if I look at this graph and now draw it in blue, and we can see it sort of curves that way, we can see that this line, well, since the coordinate of this point is x0 and that's x f of x, this line has a length of f of x, but this line has a length of f of x plus h. And this length here is the difference between x plus h and x. You can write it as delta x, but in reality it's just h. And so another key thing to note is if I draw another line in red, for example, if I draw a straight line segment connecting these two vertices on the graph, since this line is curved, what this shows me is that this area of a of x plus h minus a of x is not always going to be perfectly the area of a trapezium. But, so if I make h smaller and smaller and smaller, and I'll do that with a blue pen, you can start to see that, well, this area gets closer and closer and closer to 0. And indeed, a curved line, as I draw chords, as I bring the x values of those points that lie on the chord closer and closer and closer together, you can start to see that no matter how bent a curve is, as h becomes infinitesimally small and practically it approaches 0, a curved line tends towards being a straight line. And furthermore, f of x plus h, as h tends to 0, gets closer and closer and closer to f of x. The y values approach and approach and approaching it closer and closer and closer to each other. This area of a of x plus h minus a of x, but the limit as this tends to 0 is practically equal to, well, the area of a trapezium, or if I bring this down here, more accurately, it's almost like we've got the area of a rectangle, since this tends to f of x, and a rectangle is basically just a special trapezium, right? Because these two sides are still parallel to each other. So now, as h tends to 0, delta x tends to dx. That's kind of where dy by dx comes from. This area is basically h, or dx, times f of x. Well, if you want to use the area of a trapezium, this is just f of x plus h all over 2 times h, and that tends to h times f of x, if you really want to use trapeziums here. That limit, as h tends to 0, is just h times f of x. Since the derivative with respect to x of a of x, or a prime of x, is equal to the limit as h tends to 0 of, well, a of x plus h minus a of x all over h, this is now equal to h times f of x all over h, which is equal to f of x. And now, since a prime of x is equal to f of x, by using the definition of integration, in a way, or reverse differentiation, this implies that a of x is equal to the integral of f of x with respect to dx. But we've got a problem. Here, there are infinitely many solutions of capital F of x given a function lowercase f of x due to the constant of integration being added on, as we saw earlier, where the derivative with respect to f of x plus c is equal to the derivative with respect to x of f of x. But since I know a of 0 is equal to 0, that means I know what the exact value is. And to be even more specific, I could just say that a of x is equal to a definite integral rather than this indefinite integral here. A of x is equal to the integral from 0 to x of f of x with respect to dx. And this is equal to f of x minus f of 0. So a of x is equal to the integral from 0 to x of f of x with respect to dx. And that's equal to capital F of x minus capital F of 0. Or, to be even more specific, the area from a to b is equal to the integral from a to b of f of x with respect to dx, which is equal to f of b minus f of a. Since, well, a of x is equal to that, that would mean that this integral is equal to the integral from 0 to a to b of f of x with respect to dx minus the integral from 0 to a of f of x with respect to dx. And since that is true, you can see it graphically. This is the area of a of b and this is a of a. And since a of b, in truth, I could just say that's a of b minus a of a. But then a of b is equal to f of b minus f of 0, and a of a is f of a minus f of 0. And if you want to rearrange, you can see that a of b minus a of a by cancelling out the f of 0s is equal to f of b minus f of a. And so we are done. And that's why integration is used to work out what the area is between 2 points on the x-axis when we look at the area enclosed by the function y equals f of x and the x-axis, since a prime of x is equal to f of x. And the reason why it's my signed area is if f of x was negative, like it is here, my area function, if I was to graph a different area function, I don't know, this is clearly not true by the way, but say it is, say this is my area function. At this point here, you can see that my graph has to be decreasing because my value of f of x gets smaller and smaller and smaller. But in reality, if I'm looking at pure area of a shape, I'd have to add the area of this shape and the area of these shapes if I'm looking at the total area enclosed. But since I'm looking at the signed area enclosed from those bounds, this all seems to work. And this not just seems to work, this all does in fact work. Because, well, now, since this area is negative, my area function a of x can be decreasing at some points, at all of these points. And so by allowing us to have signed areas rather than just pure areas, which don't normally have directions, we can see that the derivative of a of x with respect to x is equal to f of x, so the area under the graph is given by a definite integral. And a nicer way of looking at this is, say I've got another function, and we're going to draw it here because I've run out of space. Say I've got this function again, but I'm only going to draw it from here. And you might have come across the Trapezium Rule in GCSE. Lines at equal intervals, and I'm going to let these intervals be h, or of length h, and we work out the areas of these trapeziums. And by the notion I've described here, the area will always tend to h times f of x, even if the graph is bending that way. Because, well, this just misses some areas of a of x plus h and a of x is now less than that area. But then again, as we draw more and more chords, this excess area then tends to 0, so then we end up with a of x plus h minus a of x tending to h times f of x. So we got this here, this sort of notion here. And then as you make h smaller and smaller and smaller, as you make h smaller and smaller and smaller, you can see that we get infinitely many rectangles of an infinitely thin width, a width of dx. So the integral from b to a of f of x with respect to dx, which is the area, well, that's just, the reason why we use this notation with this big S is, well, it's almost as if I'm adding, since I've got infinitely many one-dimensional lines, which are kind of rectangles with a width of dx, a base of dx but a height of f of x at any point x equals 0, it's almost like the area of this is equal to f of a times dx plus f of a plus h, then f of a times dx, that's my next infinitely thin rectangle, plus f of a plus 2h dx plus f of a plus 3h dx, all the way to plus dot dot dot, plus f of b times dx. That's what my integral is. I could just write this whole integral to be all of these f values added together times dx by factoring out dx. And since we're adding infinitely many values of f of x, but as we make h smaller and smaller and smaller, this summation tends towards the integral, which is why we've got that big S sign. It's almost as if it's a sum of infinitely many things, of infinitely many infinitesimal things. If I draw in infinitely many lines, you can see that we can almost get a two-dimensional shape. We can almost color in the whole area. And this, if you want to interpret it in the way I interpreted 0 over 0, this might show that infinity times 0 is equal to, well, anything. Because, well, we've got infinitely many lines, and each line technically has an area of 0. But since we're using the idea of a limit, we end up with us knowing what the exact value of infinity times 0 is in this context, for example. Because we just almost paint the whole figure and shade in the whole graph with infinitely many thin one-dimensional lines. This is why integration is used and what it is, and two pivotal ways in how integration is used. So thanks for watching this video. Please let me know if there's anything I could explain a little bit better, and until next time.